Okay, good morning Year 13. This is a bit of a jump sideways, and apologies that you're kind of looking at this in your own time, just to make sure that we don't fall behind. This section is actually all notes pretty much, and it's actually dropping down into the lower sixth for this year, so it's in a bit of a crossover year. So it's really just a quick run through on the oscilloscope and how that fits with electricity waves. Why electricity waves? Because of all the electricity we tend to get in around the world is transported as alternating current. Okay, why? Because as you flip your generator around and you get your swap in direction, the induction that comes from moving a coil through a magnetic field, the size of which depends on Faraday's law, and the direction at which it's going up and down depends on Lenz's law. That means that we always end up with electricity as AC. So, very difficult to measure with a meter. Can be done, but more importantly, this is a far better voltmeter than anything else because of the way it works. So I would get a little bit of research, go and have a look at my PowerPoint and have a think about it. You're using in here a dot of electrons that's fired from the back, hitting the screen that makes it scintillate. Okay, so you've got these flashes of light being emitted by the coating. So back to energy levels and excitation. We move the dot across the side using one of the controls, and there's two sets of controls. So it uses the time base, the time it takes to go across, and that's using a pair of electric plates. So again, our electrons are firing towards you, and they're being pushed to the left or to the right. That's always changing, so that your dot sweeps across, then jumps back, sweeps across, jumps back. So you're only seeing the end of the single beam of electrons being fired at the screen. Okay, so have a look at the pitch, they're quite interesting. However, for what we need, it's really just two simple bits that we need out of it. So if you go and look, and I'll just put it up here, so go and look at the waves topic. So the Waves YouTube channel, okay, area, whatever you want to call it. So if you look in there, the first video is using the oscilloscope to measure frequency and amplitude and things like that. Okay, so go and have a look at my video. It's only about 4 minutes, 5 minutes, and it's asking you to practice, so good little bit there. Okay, lots and lots of buttons on most of them. Actually, there's only really 3 or 4 that make a difference. So some are fairly obvious. Intensity, how many electrons are hitting the screen at a time, therefore change the brightness of the dot, make it easier to see. Bit of focusing, a bit of electric fields, don't really need to know about that. And then the 2 main things. We'll often have 2 inputs, so they're just mirroring each other. But the main one is the volts per division. So that's our vertical scale. So this is your y-axis. Okay, and that, when we're talking about a division, is literally each centimetre square that's on a screen. So that's your division. Okay, so if that's set at 3 volts per division, it won't be that, it'll be 2 or it'll be 5. But if you put on, say, 2 volts, then any wave that is 1 square high is 2 volts high. You know, it's just reading the scale off your graph. So, yeah, just a reminder of lesson coming up. So keep this nice and short. Similarly, the rate at which it goes across, so you can make your waves taller and shorter using this. You can make it wider and narrower using this one. So this is your x-axis, or should we actually say time axis, because they are both they're both on the same principle. So again, so many milliseconds per division, usually, maybe microseconds. It all depends on the scale that you click it round to. But again, you've got your time-based division. Okay, so sorry, division in time. It's not a dive. And that's really it. That's all there is that you need to know about it. So it's just literally reading a graph, and the scales, horizontal and vertical, are those. So that's all you really need to know about this. There is a little bit more which we need to link into this, because if you're measuring voltage, well, what exactly are you measuring? So we need to bring a little bit more into it. But in terms of objectives, they're fairly straightforward. Can you do stuff? Now, the crucial bit is this changes the electric field that makes our electron go up and down. So it's voltage that this measures. This is a voltmeter. Okay, so that's the crucial bit. If you want to measure current, then what you need to put in is the idea that V equals IR. So if you have a known resistance, by measuring the voltage, you are measuring the current. Okay, so you're just using a little bit of analogy there, and that's how all meters work anyway. Frequency, give an example here. So again, you can work it out, etc. But how do we use it? Well, it's just the standard equation. You're going to measure time. So the frequency is waves per second. You just need the time constant to give you seconds per wave, or milliseconds per wave. Okay, so fairly standard kind of tracing. That scale is commonly used because most things tend to be mains, and we're looking at 50 Hertz. So that's 2/100ths of a second. Right, okay, so it's probably worth putting in, I don't know if there's space there, no there isn't, so I'm just going to squeeze in at the edge that you can actually turn off the time base. So if time base is off, and you often use this in investigations because it's really handy, if you've got a wave or a changing pattern, it's a bit easier to do this. So if you turn it off, then you get no time going sideways. The dot stays on its spot, but the voltage is moving it up and down. Then a vertical line is displayed. Okay, and the length of the vertical line is simply, especially if you've got the wave that you've turned into vertical line, you are seeing, like the end view of that, you will just see that line going up and down. So you've got 2 times the amplitude. It goes from the peak to the trough, and you won't see the wobbling in between. You'll just see a nice straight line giving you maximum reading. It's quite a nice way of investigating stuff. So it gives, just to introduce the term, peak to peak value. What does that mean? Let's go to section 7. Okay, so a quick run through, which is looking at AC systems. Okay, now AC stands for alternating current, but we also talk about AC voltage, AC current and AC voltage. So it means sinusoidal. Let's go with that. So AC current, alternating currents doesn't make sense, but hey ho. Right, crucial little things is that on your voltmeter, i.e. your oscilloscope, you can just display how things change. If you have a DC value, so a direct current like a cell, it's not going to change. So if you display that, you'll just end up with a line. If you turn off your input, it always goes to the 0, obviously, because you've got no input, and you adjust it to a convenient square on your screen, and then it will jump up when you turn it back on if you've got a constant voltage. If you connect your voltage the other way around, it will jump down by the same amount. So it will give you either of those. Okay, so all depending on which way you connect your battery to the voltmeter, okay, to your oscilloscope. Whereas if it's AC, you get this. Okay, and this is our peak. And we call that the peak. I know it's a negative peak, but it's still the same size as a positive peak. So when we're talking peak to peak value, we mean all the way from the top to the bottom. It's very difficult to measure it from 0 because you don't have that, you just have the trace. So what we tend to do, like most things, measure big, measure top to top, bottom, and then half it will give you the value. Now, the peak value obviously links in, and most of this I think is fairly explanatory. However, we get the idea of root mean squared, and I think this is a really nice way of showing what RMS means as well. So, for example, let me just get a sheet of paper. If we had, imagine you could do this, if you had your sinusoidal wave, if you stuck it through a machine that magically wanted to ignore the negative. So we're just looking at, shall we say, the heating effect. Okay, so you put a bulb on a DC current, you put a bulb on an AC current, the same size of bulb, rating of bulb, and they're both the same brightness, then the electricity must be equivalent. But of course with AC it's actually turning on and off, it's swapping direction for your current as well. Firstly it's flowing in one direction, then it flows in the opposite, then the first direction, and so on. So if you were to swap it so it's just all flowing in one direction, that will be your AC wave. Okay, so we're just ignoring direction, we've got the modulus of it, the scale of it. However, we're still getting some points where the bulb will be brighter and somewhere it'd actually be off. Okay, so what you want to do is kind of flatten that out. We want to try and take those peaks, chop them off and fill in the gap underneath. Okay, so if that is the same size as that, that will be the equivalent to the DC. Okay, it will give you the same amount of brightness, it will give you the same amount of heating. We talk heating normally because all things get hot in electric circuits, whereas not all things give out light. So equivalent to DC power, and I say that with the heating is a far better way of putting it. So it's equivalent to the same value, whatever that value is, of voltage. Now that, for an AC wave, is the RMS value. Okay, the RMS voltage. So how do we mathematically do this? Chop the tops off, shove them in the gaps so it's nice and level to get the same equivalent to DC voltage. Okay, because that's what we mean. Okay, they're the same thing, but trying to get that equivalent effect. Well, we use the root mean squared. So what do? Effectively, if I just move that down to here, I've got my jump up there. Okay, so I go for the root mean square. So what we're going to do is we're going to square it. So we're going to go to much higher. Bum, 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 bum. Okay. Apologise if actually you've done it wrong. It should be that one. But again, much higher. If we find the mean of that, okay, the mean value as it fluctuates, you'll get a certain value. So it will just be like this. Unfortunately, it's now twice as big. So, or not twice as big, it's the square of that value. So if you then square root it, it turns it back again. Okay, so it will reduce it down to, so that's my squaring. That's my mean. Oops, excuse me, mean. And then if we go back to just swapping that down, that value there to the actual equivalent value there. Okay, so that's that same thing. Then here is the root of mean squared. Okay, so we have gone back to our original value. So we square it, we find what's known as the geometric mean, square them or multiply them all together, and then find the nth root of the average of the lot. So RMS is a way of converting between variations in a very effective way, mathematically kind of chopping to make everything the correct value, the equivalent value. So in terms of what's actually useful about that, and again you may get this, it's not so often done, is that you start to look at some details. So let's just put in the key point is this thing here. So RMS, as I've just put, is equal to the DC value, and it should have been lowercase on my last sheet. Okay, so the RMS value is equal to the DC value. Okay, so how does that work? Well, it's the idea to do with power in a way, because it does kind of work quite well. So if you are looking at power, okay, we can do that mathematically. It kind of makes sense. So power is, let's say, voltage across a resistor causing a certain amount of heating. Okay, that will be V squared over R. Okay, that's the idea of where you're getting your square from. So what we need to do, if you were to double one, you would actually find 4 times the value of the other. So if you wanted to double your power, you'd actually need the square root of that doubling. Work that through. So bottom line is, if you divide the peak value, let's say V peak, divided by the square root of 2, okay, then you'll get the RMS value. If you want to do that as current, you can do that as current. You'll get the same effect. But yeah, basically the VRMS equals 0.707 of the maximum value. Okay, but that is often what's quoted. So when we say 240 volts out of the plug, it's actually the RMS. It will go up to 315 and down to minus 315 and vary in between. But it's equivalent power, equivalent to a 240 volt battery. Okay, so quite a powerful idea, but it's often hidden behind the scenes. Don't think you'll get questions on that, but it's that useful way of thinking about it, because normally we need to turn AC into DC, back into DC to make it useful for a lot of what we do in the modern world.